All right, let's jump right in. We're going to take a deep dive into the world of interstellar visitors, these incredible objects that have journeyed from other star systems right through our own cosmic backyard. We'll be comparing three of the most famous ones: the very strange ʻOumuamua, the active comet Borisov, and the newest arrival on the scene, 3I/Atlas. So what can these travelers really tell us about the universe? Let's find out.
This explainer is all based on some really groundbreaking research from Nohil Kodiyatar and Abhay Shamala. These are the folks right on the front lines, piecing together the incredible stories of these interstellar objects. And their findings, they're part of a much bigger work that pulls together all the latest data and insights on our most recent visitor, 3I/Atlas. It's all about building a clearer picture of these cosmic nomads.
Okay, just a quick heads up before we really get going. The science around these objects is moving at lightning speed. I mean, what we're talking about today is the absolute cutting edge, but new discoveries could be right around the corner. So you've got to remember, this is a field that's always evolving. So what's our game plan for this cosmic journey? Well, first, we'll set the stage. Then, we're going to look at the absolutely wild paths these objects took and, what they actually look like. After that, we'll dive into their chemical makeup, what they're made of. We'll also explore their activity and what that tells us about just how many of these things are out there. And finally, we'll touch on the human side of it all, how we talk about these discoveries, and what the future of space missions might look like. All right, let's kick things off. Time to set the scene and talk a little bit about how we even know what we know.
So, what is the big deal about this third visitor, 3I/Atlas? Well, it's simple. It gave us our first pristine, high-quality look at an interstellar object that was acting like a comet, fizzing and glowing right from the moment we laid eyes on it. Chemically speaking, 3I/Atlas is this fascinating middle ground. It wasn't just a quiet, rocky object like ʻOumuamua was, but it also wasn't super rich in carbon monoxide like our second visitor, 2I Borisov. No, this one was full of water and a healthy dose of carbon dioxide, which gives us a totally new piece of the interstellar puzzle to think about.
And here's the really crucial part. Now that we have solid data from three of these visitors, we can finally move beyond just looking at them as one-off curiosities. We can actually start to see patterns, to compare them statistically, and to ask much bigger questions about where they all came from, how they're different, and what that says about all the other star systems out there.
So, what are the big questions this research is trying to answer? Well, first, just how different are these objects from each other, really? Second, do they fit into nice, neat little boxes, or is it more like a spectrum of possibilities? And third, how can we use amazing new tools like AI to get way better and way faster at studying the next one that comes our way?
To tackle those questions, the researchers went on a massive data gathering mission. They combed through hundreds of scientific papers. Then they used this incredibly powerful AI tool to pull out all the key data points with, get this, 94% accuracy. That meant they could be sure they were comparing apples to apples across all the different studies.
Okay, now for the really cool stuff. Let's talk about the incredible journeys these objects took through our solar system and, what they actually look like. Just look at the numbers in this table. Their orbital paths are, they're completely wild. That first number, the eccentricity, the fact that it's way over 1 is the dead giveaway that these things are not from around here. And check out the incoming speed for 3I/Atlas, a mind-blowing 58 kilometers per second. That tells us it was probably thrown out of its home system with some serious force.
So, by tracing their paths backward through the galaxy, we can try to make an educated guess about where they came from. Now, ʻOumuamua and Borisov seem to have originated from a younger part of the galaxy, kind of like our own stellar neighborhood. But 3I/Atlas? Its path suggests it came from a much older, more distant region. Trying to find its exact home star, though, that's like finding a needle in a cosmic haystack.
And they made some pretty close passes on their way through. Both ʻOumuamua and 3I/Atlas came relatively close to Earth, cosmically speaking. Even cooler, 3I/Atlas's close flyby of Mars on October 14, 2025 gave us a total front-row seat. We could actually use the spacecraft already orbiting Mars to snap some incredible pictures.
So what do they look like? Well, it's a real mixed bag. ʻOumuamua is just famously bizarre, right? It was shaped like a cosmic cigar, more than 10 times longer than it was wide. But Borisov and Atlas, they were much more what you'd expect. Pretty much spherical. It's fascinating how their shapes seem to tie into their stability and rotation. And their sizes are all over the place, too.
Oumuamua was tiny, just over 100 meters across, but 3A Atlas was an absolute giant at nearly 10 kilometers. And they're all pretty dark, reflecting very little sunlight. This huge range in sizes suggests that for every giant like Atlas, there are probably tons and tons of smaller ones out there just waiting to be discovered.
Okay, so what are these interstellar travelers actually made of? It's time to peel back the layers and take a look at their chemistry.
This table here, which shows the gases boiling off their surfaces, is just incredibly revealing. You can see ʻOumuamua was basically silent, nothing coming off it. 2I/Borisov, on the other hand, was rich in carbon monoxide, and 3I/Atlas, that's our water-rich comet. This diversity is a huge clue about the totally different environments where these objects must have formed.
We can learn even more by looking at the different flavors of atoms, which are called isotopes. And here's something that is just amazing. The types of hydrogen and nitrogen they found in 3I/Atlas are remarkably similar to what we find right here in our own solar system. It's this fascinating, totally unexpected connection across such a vast expanse of space. And what about the dust they leave behind in their wake? Well, looking at it in infrared light reveals it's mostly made of a common mineral called olivine. But, and this is the important part, it's not in a crystalline form. That tells us that this dust was never cooked at super high temperatures, which is another crucial clue about the conditions in its home system.
Okay, let's take a look at how these objects switch on as they get closer to the sun, and what that can tell us about the total population of interstellar objects just wandering around our galaxy. This is so cool. Depending on what they're made of, they start to become active at different distances from the sun. Borisov started fizzing with carbon monoxide when it was still way out there, about as far as Jupiter. 3I Atlas waited until it was closer to start sublimating its carbon dioxide ice. This is a direct reflection of the snow lines where different ices can form in a solar system.
So, based on the fact that we've found 3 of these objects in just a handful of years, we can actually start to estimate how many are out there. And the number is just staggering. Something like 5,000 trillion of them in our galaxy alone. With the new telescopes coming online, we're about to go from finding one every few years to finding dozens.
You know, the discovery of these objects hasn't just been a scientific story. It's also raised some really big questions about how we communicate science and how we dream about the future of space exploration. You probably remember the absolute frenzy when Oumuamua was discovered, right? All that speculation about alien technology. But look at this trend. With each new discovery, the alien chatter has gone down. A lot. And why is that? It's because the scientific community has gotten much faster and way more open about sharing data, which is just the best weapon against misinformation.
I think the key lesson from Oumuamua was about the danger of holding back data. A 13-day delay in releasing some radar information just poured fuel on the fire of wild speculation. Now compare that to 3I Atlas, where the raw data was released to the public in just 6 hours. And the result? Conspiracy theories just plummeted, and everyone could participate in the science.
So, of course, this leads to the ultimate question. Could we ever actually visit one of these things? It is incredibly difficult, mainly because they're moving so unbelievably fast. A normal rocket just can't catch them. But this research shows that new technologies like solar sails could potentially make it happen. But only for the slower ones, and only if we get years and years of warning to get a mission ready.
So what are the biggest takeaways from all of this? Let's try to bring it all together.
In the end, studying these 3 interstellar pioneers have shown us this spectacular diversity that exists across our galaxy. They've shown us that there isn't just one type of interstellar object, but a whole continuum. We've also learned some really crucial lessons about doing science openly and honestly. And with so many more discoveries on the horizon, the age of interstellar exploration is really, truly just beginning.
Of course, this entire understanding is built on the hard work of so many researchers. For anyone who wants to dive deeper, we wanted to highlight some of the key papers that really laid the foundation for this analysis. We're just going to cycle through them quickly.
First up is the foundational work by McKelly and their colleagues in Nature, which was the first to detail that strange non-gravitational acceleration of Oumuamua.
Then there's the discovery paper for our newest visitor, 3I/Atlas from Bolin and the team, which gave us our first detailed physical description of the object.
And of course, we have to mention the paper from Meech and our collaborators that introduced the entire world to the red and extremely elongated Oumuamua.
This was a key early comparison by De Leon's team, which was one of the first to put the physical characteristics of our first 2 visitors side by side.
Here's the paper from Smith, Liu, and Sharma that details the powerful AstroBERT V2 model. That's the AI tool that made so much of this new analysis even possible.
And finally, the work from Bodowitz, Noonan, and Millam, which gave us a really close look at the cometary activity of our second interstellar guest, 2I/Borisov.
The full list of references, of course, has many more essential contributions, and each one helps build our collective knowledge. I think the key takeaway is that science is a collaborative effort, and every new discovery opens up a new door. The question is no longer if we'll see another interstellar visitor, but when, and what new secrets will it bring with it.